So welcome everyone. We are here with Professor Sam Krucker in Switzerland. You can see him in the webcam, and Professor Wing Ip, the Executive Director of ESSI-BJ. Hello, Evan. Hello, everyone. And thank you for being here. And thank you, of course, to Professor Krucker for accepting our invitation. Professor Krucker will today talk about the Solar Orbiter mission. It's actually the second webinar on the Solar Orbiter mission of NASA and the European space agencies that we have. And today it will specifically be on STIX, that is a hard X-ray telescope. I won't say too much because Professor Ip will introduce Professor Krucker. I will say a couple of words about ESSI-BJ. I am Laura. If you've seen our previous webinars, you should know me, and I'm the PR manager of ESSI-BJ. ESSI-BJ, which is International Space Science Institute, Beijing, was established in 2013 thanks to the cooperation between the International Space Science Institute in Bern, Switzerland, and the National Space Science Center of the Chinese Academy of Sciences. We have our goal is to advance space science studies, so we cover a wide array of disciplines and we organize a wide array of events to support scientists and experts in the space science fields. Our events include workshops, forums, international teams, working groups, and so on. They're usually offline events. Since last year, of course, we only have online events, but we are grateful also to the scientists and experts who have accepted to give webinars, so online seminars, since last September. The series that we have today is the On Things to Come series. We focus on ongoing and future space missions, and again, we have today Professor Krucker. And we also have another series in Chinese called 1001 Space Nights, which focuses on women scientists from China. I won't say anything else because I think Professor Ip can introduce Professor Krucker to you, to the audience, and then we can start. Many thanks once again.
Yes, thank you, Lola, and welcome everybody. And we are very happy to have the second talk of the Solar Orbiter mission of ESA, today. And the speaker is Professor Sam Krucker. And Professor Krucker, he was graduated, he got his PhD from Zurich ETH, and then he went to UC Berkeley as a postdoc, and then since then he just stayed there, I said stayed there because he is now sharing a half appointment at Berkeley and half appointment here in Zurich. Of course, Professor Krucker, he is expert on hard X-ray telescope spectrometry, and I think he is the leading expert in this area. So we're very happy to have him, telling us about his very powerful instrument called STIX on solar orbiter, and of course he will also tell us a lot about this very advanced research area in solar flares. Yes, Sam, please go ahead.
Thank you very much, and hello to everybody. Let me share my screen. And let's hope that works. Otherwise, please scream. Okay, so this is the second webinar on solar orbiter. This one will focus on solar flares and how the solar orbiter instrument suite will contribute to that field. What I will do here first, give a motivation for all this and try to explain the core science behind the hard X-ray mission from the sun, so about solar flares, and then show what we already got with STIX since we are on. And what we want to do is, of course, the major part, because the main mission, the nominal mission of Solar Orbiter, will only start at the end of this year. So to start with, maybe I show this image here, which is the fleet in heliophysics, which is really quite impressive. So we are really lucky that we have this excellent coverage with many space missions and also additionally ground missions to really study our sun. And Solar Orbiter is one of the newest, or if not the newest one, that was launched last year. And here is a picture of the spacecraft where all the instruments are marked. These are only the scientific instruments. And you see, this is quite impressive, how many different boxes with instruments that are mounted on this one platform. We have instruments that look directly at the sun. So to the right, you see a cut through the heat shield, and then the instruments behind. So they look through the heat shield and make direct remote sensing observations of the sun. But then there are also many other instruments that measure in situ. So at the spacecraft, the magnetic field and the particles around the spacecraft. So this is quite unique to have a space that is unique, right? We have no other spacecraft that had such a broad range of observations. And that's also the major goal of this mission, to have everything on one platform to look at the same time at what happens at the sun, to understand the sun and the heliosphere. Of course, that also means that each of these instruments is limited in resources, which means mass, power, and telemetry. So it is also a huge compromise for each single instrument. If we would have restricted the Solar Orbiter to 2 instruments, and of course we would have had much more resources for those. But we didn't want to do that. It was really the main thing to observe together, to get as many different aspects. And for that, we had to make giant compromises for our instruments. So our instruments are very often not better than what was flown before, but they're using much less resources. And that's usually mass, power, and in particular telemetry, because we're going far away, and so telemetry is really not very high. So we cannot send back all the data we are able to take. Very often, actually, it's only a very tiny fraction, so we have to make also smart choices. So all these instruments are top-notch, but much of the development have been done by making those instruments smaller without losing too much of the science. So today, the main topic is our instrument here that is led in Switzerland, but with a huge international participation. That's called STIX, and the X is for X-ray. So this is a hard X-ray telescope. These are energies that are from a few kV up to 150 kV. And so these are roughly the same energy range. There's the same energy range that also the dentists use to look through our teeth. And so Solar Orbiter, besides having all those instruments on one platform, it's also a unique orbit. And of course, the name already says what we do. We orbit the sun, and we go closer in, because when we are closer in, we can see better, but we can also measure much better what's flying away from the sun, because it's the particles have not been that long on route to the spacecraft, so the information is less diluted. The launch was here in, that was the launch configuration, that is Earth, Venus, and the sun here, and I play now the movie. February 9th was the launch, so we left on Earth. This was the commissioning phase. And what we used to change our orbit are gravity assists. So here we flew by Venus to get thrown in closer. And the movie stopped here. That's today. So today, as you see, we are quite far away from Earth. The angle is roughly 90 degrees. So we're looking from a different viewing angle. And that's quite unique, right? This, and in particular for the STIX instrument, this opens a lot of possibilities of observations that were simply not possible before. Continue here the movie, and you see we have another Venus gravity assist, and then come back to Earth to use also Earth as a gravity assist, and that's the start of the nominal mission. And before we talk about that was the cruise phase. And you see we go in close. It's about 0.3 AU, so 30% to the Earth Sun distance. And then in the later phase of the mission, we are also going out of the ecliptic. So you see here more or less solar orbiter is still in the same plane as the planet. But then we use gravity assists to get out of the ecliptic, so we get a view of the polar regions. And that's also quite unique, because from Earth, you never really properly see the polar regions. And with solar orbiter, we go out of the ecliptic, and then with time, of course, it takes time. You see the time is running here. We are already 6 years from now, almost 6 years from now. And so by the end of the mission, you see it's a very long mission, we will get to 30 degrees out of the ecliptic. The other exciting thing is that solar orbiter was launched just at the start of the next solar cycle. So here are measurements in radio that show in time how the activity of the sun changes. And you see we were in solar minimum and now enter solar maximum. And so this solar orbiter mission is really perfectly spread over this next solar maximum. And that's, of course, really a rich source to study solar activity. And you also see that, 20 years ago, we had much brighter cycles. But nevertheless, even a small cycle with the current instrumentation will bring us so many new insights that were not available with the previous cycles. Okay, we had way more flares, but the coverage with instrumentation was much poorer. So we are happy also with this very moderate cycle that is predicted at the moment. And just to show that the solar cycle has really started, these are AIA movies from a few days ago, so that's May 7th. And you see to the left, at the eastern limb, there is an active region just showing up on the disk. And then there's an eruption. And I don't know how well the movie goes through the internet, but you can see this eruption is not located only at the sunspot where we have the stronger magnetic field, but you see that really almost the entire sun is affected by this wave that travels through the corona. So it's really, this was a moderate size flare, and that means really the solar activity is increasing, and we're looking forward for the next years where we have more flares. This is also from the same time range. This is now looking out a little farther. You see in the center, that's the sun. And then these are coronagraphs that at various levels that occults the main sun, and you see this coronal mass ejection moving outwards. So this is really the indicator that the solar cycle has started, and flares will come back on a frequent scale. And so all these eruptions and the magnetic activity of the sun creates our heliosphere. And so here is this standard cartoon that we show where we have the sun, these flares and coronal mass ejection. And then to the left, that's Earth with its protective magnetic field. And what the main science of solar orbiter is to fly through this heliosphere, make observations from different angles with a large number of instruments, and try to understand how the sun creates this heliosphere. And so today I want to focus on the X-ray instrument, and maybe very just in the beginning say, why do we see these X-rays, or hard X-rays we call them? We mean hard because it's the higher energy end of the X-rays. And it's really the diagnostic mechanism we have is Bremsstrahlung. So when electrons, as shown here, go close by an atom, then you can create Bremsstrahlung emission. And if the electrons have high enough energy, then of course that photon that is created is in the X-ray range. And so this is our main diagnostic tool that we have for these observations. And this is our instrument, STIX. And so it has three main components. So first of all, we make a hole in the heat shield, but because we are looking at X-rays, we can actually cover that hole in the heat shield with a lightweight metal, and we're using a beryllium, because beryllium is quite transparent for X-rays, but still blocks out the sunlight and the heat quite efficiently. Then behind we have these two other instrument parts. One we call the imager, and the other one is the detector electronics module. So in the back of this box here, we have our X-ray detectors. So these are sensors that measure the incoming X-ray emission and time tag them and give them energy. So we measure the spectrum as well. And then in front, we have our imaging system. And this is now something a little bit unusual. And the reason is, you know, X-rays, you know, they are going through everything. So it's not so easy to build an optic that focus the incoming X-rays. We are working on this, and that will be the future. But to build a small, compact instrument, this indirect imaging system is still the way, is clearly the way to go. So we could build with this instrument is only 6.5 kilograms in mass, and is quite compact. And so this was kind of fine, this indirect imaging system, and I'm going to explain that. In short, what we do is we have two sets of grids mounted in front of the detectors, and they make a shadow on the detector. And from that shadow, we then infer the image, or what the shadows tell us is a Fourier component. Here are a few images. That is the day when I last saw the instrument, that when we delivered it to Airbus in the UK, and it got mounted on the spacecraft panel. You see that's already quite a while ago, and you see these two components, so the imager with the grids, and back here the box with the detectors. Here is another picture just of the front part of the box, and to the right you see these detectors. We have 32 detectors in there, and there you see the shiny plate on top. That's the crystal. It's a cadmium telluride crystal that stops the X-rays, and below the block is the electronics. Here another shot where we when Swiss industry assembled all these detectors, and gives a nice overview how they are spaced out. And you also see it's quite a compact instrument, so the soldering efforts were really carefully, it needed to be done really carefully. And so here is those masks that I talked about. This is the front one. And you see we have these 32 openings. For each of the detector, there is one opening. And then you see two of the openings are special. You will come back to that later. And the normal ones, we have these fine grids. And sometimes they're so fine that this photograph is not really resolving it. And so this is material is, of course, something that stops X-rays quite well, because we want to make a shadow on the detector. So we need a heavy metal, and here we use tungsten. So these are tungsten grids that are etched. And now what we can do is put those two grids on top of each other. And so this was done at the lab. And when you look through them, you create these moire patterns. So you create a pattern, and that pattern, of course, is super sensitive on the incoming light. And you can see here that when we move around, this pattern change. And so this is exactly how we measure our incoming X-rays. Of course, we are not moving around, but the instrument is fixed. But depending where the source location is, we get a different pattern. And that's how we reconstruct our images. And this is roughly explained here. So you see to the left, schematically, the two grids that we look through, and they make a pattern on the detectors. And we made the pattern in a way so that it perfectly falls on the detector. And then we have 4 pixels that measure the position of this maximum. And for a source that is on axis, we see it, let's say, it also in the center of the detector. If that source is slightly shifted, then we measure a shifted position of the maximum. And if you do that in a mathematical way, you can show that this corresponds to the measurement of a Fourier component in one direction on the sky. And so, because it's only one direction, so we have then 3 detectors with the same pitch, but with different orientation, so that we measure that Fourier component in 3 different directions. And then we have 10 different grid pitches. And so if you go back to the previous explanation with a source and the maximum, that explanation works if we have a point source, which means the source is much more compact compared to the grid pitch. And you can just imagine, if you have an extended source, that corresponds like a chain of sources. And of course, they would produce a pattern that is shifted depending on which pearl in the chain you're looking at. So that means it's smeared out. And to the extreme, if the source is very large, then that smearing out is perfect, and you just get a constant signal. So by having different grid pitches, which means different slit sizes, we can actually measure the source size that's happening. And we know that because if the source is too large, then we get just a constant signal, no more pattern. If we totally resolve it, we get the full modulation. And so with these 30 Fourier components, we can reconstruct the image geometry. And so here's, for example, real data now for 4 different detectors out of the 30. And you can see for the coarse one, we clearly see the full signal, while for the compact one, you see there's no more signal there. So that means for this flare, the source size was somewhere in between. And so this is a shot that we create on our website, which is just raw data, where we show all detectors and all the pixels. And for redundancy, we always have not only 4 pixels, but we have actually 12 pixels. So 2 sets of large pixels and then some small pixels as well. And this is done for redundancy, because this kind of imaging really lives, or you can improve it significantly if you have redundant information in there. Redundancy we already use by, for example, having each grid pitch at 3 different orientation. In principle, you could say 2 would be enough, but if you have 3, we have redundancy, and we can use that to self-calibrate the instrument. And I show this image here. This is from one of our flares. You clearly can see that we see that pattern in even in the raw data. So all these pixels here, you see the top of the top row and the bottom row observe the same. And we see there's the maximum here, and for this one it's here. And here also the resolution elements written here. So this is 42 arc seconds. And you can see for the top center ones here, these are our fine grid pitch. Here we don't see much of this modulation. And so that means this is again a source that is extended that we see here. So this tells us that the imaging is working. And what we have been working on for the last year is to properly calibrate now these images. So to know what really, we have to measure our grids on ground. What is really the pitch and orientation, and what does it mean to have a peak at this location? And once we have done this calibration, we are not yet finished with that, and then we have a full imaging system available. And so to conclude with this, how STIX works, here are the point spread functions. And because we only have 30 Fourier components, they don't look great, of course, right? So this is not a high dynamic range imaging system. For everyone that likes radio astronomy, they have seen this type of UV coverage pictures. So here, is the same for the STIX. So we have this spiral version here. And the outer points are the ones with the highest resolution, and then the inner ones are lower and lower resolution Fourier components. And then we can combine those and make this point spread function, and the top version is when we weight all these points the same way, and this is our point spread function. You see the color scale. So it has really a lot of side lobes. So it's not like an optic where you have a smoothly decaying point spread function. So this is not very clean. But then we use a lot of algorithms to then make our images look much cleaner. The same way I can also make a different weighting of these Fourier components, so give more weight to these outer ones, and that can make a much narrower core of my reconstructed image. But then you see that even increases then the noise even more. And so the other thing we're working on is focusing optics, where the X-rays are truly focused on a detector that has many pixels. And of course, with this type of instruments, we will get a much better point spread function, and so that might be the future. But today I will concentrate on STIX. So let's come to the science diagnostics. So what do we really see in this hard X-ray range? And to the left, you see a hard X-ray spectrum. So the units here, again, these kilo electron volts, keV, and STIX observes from 4 to 150. This is a spectra taken by the ISSI spacecraft. What you see in red is a thermal component. And if you go back to our cartoon of Bremsstrahlung, so the emission depends on what is the electron distribution, and of course also how many targets I have. And that is then really tells us how bright this emission is. And you can have these electrons that are around there. If you have a thermal distribution, then they have a Maxwellian distribution, and they produce, of course, a Bremsstrahlung emission. And if the energy is high enough, then that happens in the X-ray range. And so this is this steeply falling spectra here in red. Over here, we have also some line emission from iron-nickel atoms that are present as well. And so you see, this is an extremely steep spectrum. So it's a log-log plot, and it still dives really steeply. And if you look at this temperature here, 30 million Kelvin, that corresponds roughly to 3 keV in average energy of the distribution. And you see here, the measurements out here are done at 20, 30 keV. So that means this is far out in the distribution. So only the electrons in the Maxwellian distribution that are way in the tail, so the center energy is 3 keV, but to produce, of course, a 30 keV photon out here, that means the electron needs to have at least 30 keV. So what we observe in hard X-rays is really produced by the tail of the Maxwellian distribution, even the thermal emission, so it's really the tail. And then further down here, if you go to higher energy, suddenly the spectrum gets flatter again and has more a power law shape. And so that means there are electrons there that are well out of the Maxwellian distribution. And so these are then electrons, to make a 100 keV photon, I need at least 100 keV electrons, in average more like a 200 keV electron. And so this, of course, doesn't correspond anymore to a temperature. Also, that the spectrum we see here is more a power law. And so these electrons are produced these hard X-ray emissions are produced by accelerated electrons. So these flares appear not only to heat coronal plasma to quite high temperatures, but additionally they also accelerate the electrons. And the good thing is with this Bremsstrahlung mechanism that we have here is we understand it relatively well, so we get quantitative diagnostics. Besides the spectrum, we also get imaging, right? So we know where those emissions come from. So the thermal spectrum, that's generally what we see in flare loops. So this is from a flare that is near the limb. So you see it from the sides. I see a flare loop here. And the non-thermal emission is most prominently from the chromosphere. And that has to do with that the emission is higher where you have higher density, because that's where you have the ions. And then in addition, we can follow this in time. So this is a time evolution. This is 1240 to 45. So this is a moderate sized flare where that heats up here in a few minutes. So it's actually rather a short duration flare for this size. And then you have a decay phase that is often dominated just by the heated plasma is now cooling down. And what we frequently see is that when we have the most efficient heating, that's when we also accelerate most efficient particles. And that's, of course, understandable. When you release most of the energy, and the energy comes from the magnetic field, then you have the best chance of accelerating electrons, but at the same time, you can also heat most efficiently. And so, of course, what is different between the thermal emission and non-thermal is the thermal emission shows you the heating, right? So something gets hotter and hotter, and that's why it's rising. The acceleration profile here, that's more the heating rate, because when you heat the most, that's when you also release the most energy, so you can accelerate the particles the best. And with all these diagnostics together, we can then estimate the flare energy, right? How much energy is needed to heat that flare loop at peak time? Or we can ask, how many electrons do I really need to produce this hard X-ray emission that we see at the highest energy, so the non-thermal ones? And so if you do that, it's really obvious that that non-thermal emission is really prominent, which means these flares are really good in accelerating particles. And so it's not just a small fraction of particles that get accelerated, but these particles, they gain a lot of energy. And compared to the total flare energy, that can be up to half. So these flares are not only releasing energy, but they're really good accelerators. And it's really the case if you would have asked someone in the 50s, before we had the first hard X-rays observations, what would you expect to see? I think almost everyone would have said, yes, we see this very hot heated plasma. So it means the spectrum, the red curve. And then if you would have asked, do you think maybe these flares could accelerate particles? And said, yeah, maybe a 0.5% or even less of the energy goes into accelerating particles. And that, if you do that in the calculations, your blue curve would be way down here, maybe not even visible on this plot. And so this is really the surprise, I think, from the observational point, even if I was not alive when that was discovered. But I could just imagine to see this spectrum for the first time and say, why is it so bright? And it simply means that flares are so efficient in accelerating electrons. So it's quite an interesting problem that to study here, how such an efficient conversion of magnetic energy into accelerated particle is possible. And this is our standard flare cartoon, at least for large eruptive events, what we think what happens. So you have an expanding bubble that gets ejected out, and behind there you reconnect magnetic fields. And if you reconnect magnetic fields, you change the topology, you change the energy content in those fields, so you can make them less complex, which means they can release energy. And through that process, we release energy and accelerate particles. How this really works is, of course, still a large debate. Is it really electric fields that create up here in this point where do the reconnection? Most probably that happens, but it's not very relevant for that. Are these particles maybe accelerated as these field lines snap back? And then you get the first Fermi acceleration in there. Yes, also possible, but not the final answer. Is it turbulence that accelerates those particles? Do we have termination shocks that can accelerate particle? So there are many options there, and we are still trying to figure out which one is really the one realized. And if that go back to the image I showed before, so this is the main thing we observe, right? of these pictures in hard X-rays at least. So sometimes we see this part over here as well in thermal emission as this ejects, but generally this is the more typical thing we see. And this is partly to do with our limited dynamic range with the imaging system that is an indirect imaging system. And so if we do a quick calculations, we think really that the particles are, at least some of them are accelerated here. And so if they travel down those field lines, it's very clear that, so this is this extrapolation of a simple model, that as soon as you enter the chromosphere, you get so much brighter emission than in the corona. So it's no surprise that we see those emissions. And any emissions that would be produced on the way as the electrons travel down here should be there, definitely, but it's at a very low level. And so maybe roughly we could say, okay, instruments have problems to see anything faint below this dashed line as a sketch here, right? This is not really hard science here because it depends from event to event. Nevertheless, sometimes we actually see signals from where we think the electrons are accelerated. And these are cases where acceleration are maybe most efficient, or where acceleration happens in a way that particles are trapped long enough. Because the simple calculation, of course, only are valid when electrons just freely stream down here. If they get trapped up here, they stay longer there, and that, of course, enhances the Bremsstrahlung emissions significantly. And so we have quite a few of these observations. The most famous one is, of course, the Masuda Flare. Here I show my own observation of it from a few years ago. These are observations done by René, where we see a flare at the limb. And so you see the classic foot points. One is much fainter, indicating probably one of the flare ribbons might have been just behind, so we don't see the full emission. And additionally, see the nice flare loops that we see in EUV, but also in X-rays here. And then this flare had a surprisingly strong source again above that. And that, of course, is exciting because we think that's, compared to our cartoon, that's where the reconnection happened. And so that's within that area, somehow, the extended area of the reconnection, we think that particles are accelerated. And then we can measure the different spectra here and get quantitative measurements of that. And so this type of observation then triggered a lot of modeling. I show here just one movie of so-called multi-islands development. Their calculations are done so that always two current sheets are shown. But that's easy to calculate, but that's not really why there are two. And you see here at the start, and then you see the currents and how electrons behave in there. And then here is another plot, and I think this time it's really the number of electrons that you see that are curated. Initial models were in 2D, and then future models in 3D. And what showed is that actually the 3D thing works quite nice, because now you have a 3D structure, so electrons can jump from one island to the next and then get a more volume filling observation. And that's, of course, then a candidate that could make such bright hard X-ray emissions up in the corona. Another very nice diagnostic tools are microwave observations. There we see gyrosynchrotron emission from flare-accelerated electrons. And so these are observations from Nobeyama of the same flare. And you can see, we see electrons in radio. These are the gray image here. So you see that makes sense, but we do not see really emission from up here, which is still quite puzzling for me. Maybe it's really simply at lower frequencies where we would see it. More recent, BEIJING published a paper where we were quite lucky with observations from ESA and RESI. It's more or less the last good RESI flare. Again, it's something partially occulted at the limb. You see here one foot point, the other one is not visible. And we see one of those extended sources. And now with radio observation from EUCLID, we had many frequency, full frequency coverage over a wide frequency range where we could measure that. And now we can use the diagnostic in combination, so Bremsstrahlung together with gyrosynchrotron. And so this over here is the result. And this is now in electron densities. So this is not a hard X-ray spectrum or so on. So this is really electrons within this source. And we could constrain that the slope here and then show that to make the radion hard X-ray data match, actually the source is really bright or full of electrons up to slightly above 100 keV, but then to make the data match, it must decrease really steeply. So there's a power law of 8.5. That's super steep. So that means it looks like the acceleration happens quite efficiently here. It is below 100 keV range, but then not above. So this is something quite new diagnostic. I think it's the only event so far we could do that. And so with STIX and EOF, so we hope that we can do many more of these events to explain. And then, of course, the question is, where are the MEV electrons coming from if it's not accelerated within this region over here? And for the first, the flare I showed you from May 7th, we do actually have joint observations with STIX and EOF. So this is quite exciting. And then very often we look at flares that are not only at the limb, but actually behind. And that, of course, then that blocks the emission from the very bright chromosphere. And then we can see the much fainter emission up in the corona. And here is a cartoon of that. And if you look at flares like that, you see indeed there is a very faint non-thermal component up here as well. And maybe just looking at the spectra is not super convincing, but what we can do, or could do with RESI and will do with STIX, we can then actually follow that little faint tail in time. And then quite clear, this looks like a normal flare, except here we don't see the foot points, we see the stuff in the corona. And so that is really a clear indicator that the acceleration is, or at least the corona is involved in accelerating those electrons. And this is, of course, something that we now can play regularly with STIX and Earth observing X-ray telescope. Before, when we looked at this type of flares that I showed before here, this is super interesting. We see now the very faint emission, but we are totally blind towards the full flare emission. And so with a combination of STIX and Earth observing instruments, we now have, for at least a few flares, both the occulted and the full flare. And of course, we are really looking forward to the launch of the Chinese ASOS mission, where we then really can do this even with imaging. We have also the GCAM mission that is already up, and we are looking at the first events to compare STIX with their observations. And so with these two observatories, we should be even this year have first events where we have this occultation. Then from the Indian side, India will launch Aditya, a mission to L1 with many instruments on it. And in particular, they have hard X-ray spectrometers, so no imaging. But nevertheless, if we know the geometry, we can play this game as well with occultation. And so that's quite exciting. Missions that are already up, Fermi, we do this. And we have also we won some observing time with the new star telescope that normally looks at astrophysical objects, but occasionally also points to the sun. And one proposal that got accepted is to chase some of those occulted flares. And this is one event that we already saw that was on the commissioning phase when we had this from Earth. We saw the full flare, but solar orbiter saw only the very top. And you see there's the normal heating of the flare. And we saw this very faint emission from higher up even at the quite non-thermal energies here. And so if you look at the data from Earth, so we see the CME is right at the limb as it escapes. But from solar orbiter, we know, of course, we have a different viewing angle, but we know that we cannot see that part. We can only see the top of the CME. But if we do this game with comparing the timing, we see that the STIX emission starts roughly when the top of the CME becomes into the field of view as orbiter. And so we think these electrons are really produced not in the flare itself, but or maybe produced in the flare, but escape within the CME, and these are electrons that are trapped within the CME. Another quite interesting topic is for flares that we see from different viewing angles. And that's schematically shown here. So here for both spacecraft, one would be STIX, the other one would be the hard X-ray imager on ASOS. And but we should see quite different spectra in the non-thermal range. And this is partly because we have the effect of albedo. So that means these hard X-ray foot points, they happen quite close in the chromosphere, but nevertheless there is a certain distance to the photosphere, and a part of the emission is reflected. So any single observer always observed a direct component, which means the foot point itself, but also the scattered albedo component. And as we know the physics of this scattering, we can estimate how the spectra should change. And so we could do that already with the observations from Earth. But now when we have two spacecraft, we can really pinpoint that down because we have different look directions. And in addition, we can then reconstruct also and say, what is really the directivity of the hard X-ray foot point? And if we have indeed beaming, then we would actually expect that if these electrons come down and when they produce the hard X-rays, they have a preferred motion, then the hard X-ray emission should also have a preferred motion. So this is quite detailed science we can do, but we're really excited about this. And then to come back to solar orbiter, here is maybe the case where we want to really use the full advantage of having all the instruments on board. And this is for events when we see not only the flare, but we see particles escaping from the flare side, and they are then detected by solar orbiter. Of course, this requires that solar orbiter, by chance, sits on the field line that is connected back to the flare site. But of course, this should happen now and then, and this gives us then quite a unique way of testing our understanding of these flares and also testing our understanding of the magnetic connection. And so here, these are observations from the past, from the Wind spacecraft. Some of those, the spacecraft sits out here and suddenly they see a beam of electrons coming and then going away. You see clear dispersion here that the high energy electrons arrive first. And this indicates that these electrons are traveling more or less scatter-free away from the sun. Then we can connect that back to the flare. And these are observations from the EPD team, so electron observation solar orbiter, and these are in the energy range of, this is 10 keV, so 20 keV. So these are in the same range of electrons that we know that produce the hard X-ray emission. And if you just plot them normal as they observed with the time and energy here, you see them high energies arrive first, and you see this dispersion here. And then you can invert this and plot it not as energy, but 1 over velocity. And that gives you more or less straight lines, and the extrapolation tells you then when they left the sun. So we have not yet, because we have not yet seen a really prominent event to investigate the flare side. So here I show data from the past. This is from RESI for one of those events. And here we saw 3 foot points and then a thermal loop and another one next to it. And generally, if we see this type of geometry, we think we have this so-called interchange reconnection scenario, which is shown over here. You have emerging flux. It reconnects with the previously opened feed line. It closes down that feed line to create the flare loop, but opens the previously closed field line. And if I overplot this cartoon on the observations, you can see, yeah, that more or less matches. And then EUV observations of this often show jets. And so this is the animation of this. This was from way back from Trace. The cadence was not great, but you clearly can see this follows roughly that picture. That's, of course, quite interesting also for in situ science, because this tells us, at least for this time, we know our magnetic connection back to the sun. And that lets us then test our extrapolations quite well. So to conclude, to say, okay, show a few more data from STIX. So we have a website that is given below there. Please don't log on now all at the same time because it will break. But here I show you the activity we had over the last weeks. So this is quite nice with some big flares. That's the flare I showed before. That's an M4. These are maybe C-class flares over here. So quite active. This is a plot from observation starting January. So STIX is now on all the time, which is a much enhanced science output than initially foreseen. And that was made possible because we had extra telemetry, or the solar orbiter mission in general had extra telemetry, and some of it was decided to be spent on having STIX on all the time. And you see here, initially activity was rather low. These were all AB class flares, maybe a few C class flares in March. But now in the last months, it really picked up and we had quite significant activity. So this type of plot makes me, of course, super happy to see. This is what we were working for the last 10 plus years. Here's an automatic analysis. Just we take those flares, at least the ones that have been downloaded, and determine peak temperature and emission measure. And you see, we really, so far, we had a whole spread from flares. A class is the smallest we can see, and so far it's 4 orders of magnitude of different sizes. So we had no giant flares yet, so that will come in the next years. And then, of course, we're getting used to comparing data that are taken from different look directions. So Earth is here, so that's what we were used to, and now Solar Orbiter gives us a second viewpoint. And that's one of our flares from Solar Orbiter. From Earth, it looks like this. You had a little flare here on the disk. Solar Orbiter was in closer, so that means the sun appears larger. And of course, it's a different viewing angle, so the same flare happened over here. So we can now then, and this is just to demonstrate that our spectra works. So we look at the impulsive phase of the flare, where we indeed see these non-thermal particles as well. And later on, it's mainly thermal. And so here, then, our first imaging try. We are not finishing with this yet, so this is very preliminary, or not done properly imaging. But you see what we can do now. We see the flare from Earth. So there's a flare ribbon over here, connected by these red loops. And here, the green curve is just a semicircle to kind of give us an idea about the geometry. And then this is the same scene from, sorry for that, the same scene from Solar Orbiter. So what we can do is, we know the flare ribbons, they are in the chromosphere. So we know the altitude, and that means we can rotate them roughly what we see from Solar Orbiter, right? These are these points here. With the loops here in red, we can't do that because the loop is a 3D thing. And so we don't know the altitude. So just simply the rotate works only as a very, very rough approximation, or not at all. And so we don't do that. But what we started doing is have a reference loop in here and show the same reference loop from this other loop direction. And so that helps the to understand we can study the release of magnetic energy.
Oh. Sorry.
And they are surprisingly efficient particle accelerator, and hard X-ray and also radio diagnostics are really the tool to look into that. And then just to end up on an exciting note, it's really amazing how great a coverage we have now, not only with Solar Orbiter, but with the entire fleet and the ground-based telescope. So you're very well prepared to make new discovery for the coming solar cycle. So I'm very excited about that. Thank you.
Yeah, thank you so much, Sam. That was a very, very detailed talk. So I can see that there are some questions for you. But before you look for them, I want to ask you, because in your talk you did not mention about the cooperation with the Parker Solar Probe, because it is also flying now.
Yeah, of course, I didn't mention that except here, maybe on the last point. Of course, this is a very big asset in combination with the in situ measurements from Orbiter. We have another set taken even closer, which means even higher sensitivity to see much smaller events as well. And so that will be a very great asset for joint observation.
So we can see questions there now. Yeah.
So we indeed have some questions. The first one is, if we estimate the total thermal energy of flares, is it enough to hit the solar corona?
Yeah, that's of course always, that is one of the big questions, how to heat the solar corona. And the flare heating is one of the candidates that has been around forever. And we cannot really answer the question yet. What we know is from statistics, big flares cannot answer them. Cannot heat the corona. Would also make no sense. You cannot just have one big explosion and then heat the corona for a solar cycle. But the small ones, yes, that's the big question. And then are they frequent enough so that the sum of all the small ones could heat? This is still under investigation, and there are hints that there are really a lot of small ones, but the instrument sensitivities are still not there to really see these smallest flares. So we're still very far away from that. Nevertheless, it's still an explanation that this is a viable candidate, but it will take significant more research to really prove that, conclusively at least.
Thank you. We then have a question saying the same for the non-thermal energy. Can it explain particle acceleration by the sun?
Well, this is what we see in hard X-rays are the electrons, right? We have a very good diagnostic of electrons, in particular if we combine them with the radio. So this is one key study that we are quite far advanced from the observational side, and theory of course has some explanations. The observational case for ion acceleration is of course much more difficult, because there we only get signatures at much higher energies in the gamma ray range, and there the observations are so much more harder to do. You need bigger instruments, which means normally you don't get your few hundred kilograms of instruments that you would need to do the gamma ray observation. So there's a big hole in our understanding, quite well covered with the electrons, but the energy in accelerated ions is much less studies with the few events we have.
Do we still need to look for another mechanism, qualitatively or quantitatively?
Another mechanism for?
That is not specified, but it's part of the previous two questions.
Of course, I mean, is it about coronal heating? Of course, I mean, there's still the other options of heating the corona. You heat the corona not with releasing and accelerating, releasing energy and heat and non-thermal particles, but you can heat them with flares, and there's a whole community working on that problem as well. And I would not say that that one or the other is more likely.
Thank you. Is the angular resolution of STIX the same for all energies? How about the time resolution?
Yes, that's true. I mean, the angular resolution is given by the how fine these grids are and how the separation between the two grids. So that's then the same for all energies. Of course, we reconstruct images, and the more counts we have, the better we can reconstruct an image. And so from that point of view, we will make better images at low energies than at high energies.
Thank you. Can STIX detect nanoflares if they are not too small?
Yeah, I mean, what we see is A-class flares. And so normally we label them loosely as micro flares. So this STIX is not made to see much smaller flares than that. So from that point of view, if you talk about nanoflares, which means will we expand our sensitivity? No, we don't do that. So instruments like NuSTAR, on the other hand, have really expanded our knowledge on small X-ray flares, at least, by 4 orders of magnitude below the A-class level. So that's not going to be able to achieve by STIX by far.
Do you have any cooperation plans with China's ESA's X-ray solar telescope and the Indian Solar Observatory at the L1 point?
Yeah, so we are in very close contact with the Purple Mountain Observatory on their instruments. And also from there, we are working with, as I mentioned, the GCAM observations. And so we are always looking for other observatories becoming online. So please contact us if you're interested in this different viewing angle that the solar orbiter STIX can provide.
Thank you. Can we also observe ion beams?
Yeah, I mean, that's the problem I mentioned in the earlier question, that to observe ions, we would need to go to the gamma ray range. And so from the simple answer is no, in the hard X-ray range, we are not getting any constraints or diagnostics of ion beams.
Thank you. How can you narrow down and pinpoint the location and size of the acceleration zone in the reconnection region?
So it's really the initial problem is a dynamic range, right? As I pointed out, we see then not the acceleration region in channel in most brightest, but when those particles impact the chromosphere. For those cases where we use occultation, we have pinpointed it down, yes, but the resolution, of course, to compare it with these modeling efforts is moderate. So, but we're getting there, and I think with the combination of radio and hard X-rays, we will make quite good progress in the next years.
Thank you. Are all 32 detectors of STIX and other segments working well now? Are there any serious technical difficulties?
No, all detectors work fine. This is really amazing. We have 32 detectors, and each detector has 12 working pixels. So this is amazing. Yes, I'm quite happy. Technical difficulties, yes, of course, we always have some little hiccups, but I think nothing that really impacts currently the science. We had, we still have time to get ready for the nominal science phase. So currently, our data is open to the public in FITS files, but there are still some little things in there that are not perfect yet, and so we are working on that. But all over, I'm really super happy how the instrument works.
Thank you. And then the final question, not only because the time is up, but I see no any further question. Some theoretical models show particle acceleration by shock waves. Can it be observationally related to flares or coronal mass ejections?
Yeah, it depends on which shocks we are talking about. If the shocks of the CME, when they move out, there the ambient density is really low, and so Bremsstrahlung is awfully inefficient, and so that's super tough, if at all, at least for a STIX type of instrument, we do not have the sensitivity. Maybe for instruments that use focusing optics, this will be possible. Within the flare cartoon that I showed, of course, you have also shocks there when the reconnection outflow impinges on the coronal loop, the previously formed loops. There you can have a termination shock. And there we have, there are quite some papers on particle acceleration there, in particular if you combine the hard X-rays with radiodiagnostics.
Thank you very much. If Professor Ib has no further question, I think we can finish it here. Thank you very much once again, Professor Krucker, for the outstanding presentation that was recorded as usual and will be available online or on Friday, tomorrow or on Friday. We will have our last webinar on the Solar Orbiter mission next week with Professor Sami Solanki. I have added a link to the chat box in case you want to register. And again, it will be on the Solar Orbiter mission, but it will be on the polarimetric and helioseismic imager of Solar Orbiter. And then we will have finished our series. So thank you, everyone, once again. Thank you, Professor Krucker, and wish you a good day. A nice day.
Sam, thanks very much. Thank you.
Thank you. Bye-bye.
Thanks, everybody, for listening.